just to finish up with a final exam style question, we're going to look at this great example of, the system of pendulums. That's basically a system of masses suspended from strings. It's known as Barton's pendulums, and I've drawn them below. It's consisting of a heavy driver pendulum, which we've labelled D, and then a number of pendulums of smaller masses with different lengths, which we've labelled W, X, Y, and Z. So this is our driver pendulum, labelled D. Then these are these other pendulums I was talking about. And we see that they've got different lengths. That's 0.3 meters, this is 0.1, 0.2, 0.3, 0.4. They're all pendulums, so they're all free to swing. And in, this way, that's in and out of the page. There's nothing stopping them doing that, swinging however they want. So, but what we're going to see is that what actually happens is that basically you pull this driver pendulum out, you displace it, and then you just let it go. It's not a forced oscillation for this driver, it just swings at its natural frequency, but we'll see in a second what happens to these other pendulums when we do that. So of W, X, Y, and Z, which one of these has the highest natural frequency is our first question. And the answer is it's W. W has the shortest length of the pendulum, remember? And remember that the period t was 2 pi the square root of L over G, where L is the length of the pendulum, and G is just gravity. And so what we see is that means, well, F is 1 over T. Remember that? The frequency is always 1 over your period, and your period is always just 1 over your frequency. And so the frequency is 1 over 2 pi the square root of G over L. And so it's bigger for L smaller. The smaller L gets, L goes down, F goes up. So we want our shortest length, which is this one here, where L is 0.1. So that's the shortest frequency. There's the shortest length, so it's the greatest frequency. Now they want to calculate the natural frequency for the pendulum X. And how do we do that? Well, again, we just use this formula, right? The natural frequency is, remember this is the natural frequency. We find that it changes slightly under air. The natural frequency, as you remember me saying, the natural frequency is a little bit slower. It's a little bit less. When you're under your period is a bit longer, your natural frequency is a bit shorter. When you've got resistance, remember here this is actually going to be air, so we're going to have this damping force acting against, you've got basically drag acting against their velocities, but it's going to be very small. So that's not going to be quite the frequency it would oscillate at, but it'll be close to it. So they want us to just calculate the natural frequency for the pendulum X. So let's do that. It just involves putting numbers into this. Well, first of all, we'll see which one X is. We see that X has L equal 0.2. So this has got L equals 0.2, so we just put that into here. It's 1 over 2 pi, the square root of G, which is 9.8, we're going to take it to be here, divided by, well, L is 0.2 meters, because remember we're just working for this.
Hey guys, to continue watching this video and unlock hundreds of other super concise and exam board specific A-level physics videos, just click the Snap Revise smiley face. Join me today, and together let's make A-level physics a walk in the park.